Hey guys, Ms. Peterson here, and welcome to our AP Physics 2 Lecture 5-3, all about electromagnetic induction. In this lecture, we're going to be going through Ampere's law, Lenz's law, and Faraday's law, which are just a set of equations that govern how electricity can be used to create magnetism and vice versa. So let's get started. First, Ampere's law. How does current create a magnetic field? Well, we've talked about how moving charges create a field, and if you're thinking about current, all a current is a consistent movement of charge. So that creates a magnetic field around the wire. Now, the equation for that one is that the magnetic field, equals mu naught over 2 pi times I over R. Okay, now this one is on your equation sheet in the electricity and magnetism section right down at the bottom here. Okay, so B equals mu naught 2 pi R over I. But what is this constant mu naught? Well, luckily, that one's also on your equation sheet. Okay, that one is called the vacuum permittivity. Okay, guys see it right there? So the vacuum or vacuum permeability, basically how much a magnetic field can permeate in a vacuum. And we use this even for air, because air at this level is close enough to a vacuum for these purposes. So, like I said, B is the magnetic field. Normally in units of Teslas, okay? I is going to be the current in amps. R is the distance from the wire where you're measuring the field. Okay. And yes, it's R for distance. You can think of it as the radius from the wire. And like I said, that mu naught is the vacuum permeability. And it's equal to, and I already forgot it, 1 times 10 to the negative 7. Okay, 4 pi times 10 to the negative 7 Tesla meters per amp. So 4 pi times 10 to the negative 7 Tesla meters per amp. And you can see, of course, then how those units cancel out with our distance being in meters. So the meters and amps cancel out, and we have our units of Tesla. Now, to find the direction of the magnetic field, we're going to use our right hand. So the rule for the right hand rule for direction of current is that your thumb, okay, if you look at this image right here, your thumb points in the direction of the current, and then your fingers wrap in the direction of the magnetic field. It's a circular field created by the wire. So that's what you guys are seeing here. Often we'll do it with wires going like left to right across a page. So if we put our finger going in the same direction as that wire and then curl our fingers, we can see where the field is going into the page below the wire and out of the page above the wire. Okay, that's this image right here. Again, thumb in direction of the current, and then it's direction that your fingers curl. Where if you go from behind, that X again means into the page. We can go ahead and label that. Okay, again, the X means into the page. The magnetic field is going into the page, where here it means that the magnetic field is coming out of the page. Work it in those 3 dimensions for our magnetic fields. So here, that's showing the wire with the current going into the page. So if we put our thumb going into the plane of our paper or of our screen, whatever you're looking at it, put your thumb going in there, and then you see your fingers curling around clockwise, showing that direction. Okay? So you guys can see that in some examples here, we see the current going in, which means the magnetic field is coming out at the top and going in at the base. If we picture this as a curl of wire, okay, you can also put your fingers in the direction of the coil, and then your thumb gives you the direction of the current. So just like the current gives you the direction of the magnetic field, we can use the direction of the current. Oh yeah, the direction of the current gives us the magnetic field. We can switch which one our thumb and our hands are. So if we're looking at a coil of wire, we can have our fingers be the current, and our thumb will tell us the direction of the magnetic field. So say we look at this coil of wire. Okay, we can see that our fingers are curling in the right-hand direction, so the magnetic field will be going into the page. You can also look at it in terms of like a positive charge moving, because current is the direction of the positive charge. So if we use our first right-hand rule, the one with the force, up at the top of that loop, okay, so up at the top of that loop, we'll have the velocity going in that direction, okay? And so then the magnetic field, so inside the wire of that coil, the magnetic field will be going into the page, and on the outside of the wire, it would be coming out of the page. And we can amplify that by using multiple loops of wire. Okay, as you see here, if we have lots of loops creating these magnetic fields, we're able to generate an electromagnet. Okay, that is the basics of an electromagnet, using those moving current to create that magnetic field. And if we have less current, we have a weaker field. And if we have stronger current, we have a stronger field. Okay? So that's the electromagnet. We can also see, we know that the moving magnetic fields can create the current. And yeah. So let's do some practice. What direction would the magnetic field be around each of the wires? And the arrow is pointing in the direction of the conventional current. So again, we can either use our thumbs or our fingers. They're kind of interchangeable here, but we put our thumb in the direction of the current. Okay, so go in that direction, and we look at the way our fingers curve. So our fingers are going to curve into the page above the wire and come out of the page below the wire. Okay, where if the wire is going up, it's going to be going into the page on the right side of the wire and out of the page on the left side. Okay, and then for this one again, we can treat our fingers like the current, put our fingers in the direction of the current, and if my fingers are roping that way, my thumb is pointing at me. Okay, my thumb is pointing out of the page. And it'd be going into the page around the wire. Okay, cool. Okay, cool. So we got the direction down. Let's look at an example with the magnitude of it. We have a long straight wire going through the origin, is carrying a current of 3 amps in the positive Z direction. Okay, so if we're kind of picturing our like X, Y, Z being positive there, that would be the Z coming out at us. So I kind of picture that is coming out of the page. So I'm going to draw it like that. So there's my wire, and the current is coming out of the page. That's the positive Z direction in my kind of brain. Z and X are in the plane of the page, and then Z is coming out, or X and Y are in the plane of the page, and Z is coming out at you. So that's that positive Z at a point 1.25 centimeters away. So this distance R is 1.25 meters on the positive x-axis, okay, which is kind of how I drew it. And the current going in it is 3 amps, okay? Find the magnitude and direction of the magnetic field. Well, if we want to know it at that point right there, we can just plug it into the equation. Okay? The equation is that the magnetic field equals mu naught over 2 pi times I over R. So plugging in our volumes, we have 4 pi times 10 to the negative 7 Tesla meters per amp, right? Let's double check that units real quick. Okay, Tesla meters per amp times the current, which is 3 amps, okay, divided by 2 pi times R, which is 1.25 meters. So we can see the meter units cancel out, the amp units cancel out, so we're left with units of Tesla. And when we plug that into our calculator, we could cancel out the pi's if we wanted, make our math a little easier, but I'm just going to plug it in. Okay, we got 4 pi times 10 to the negative 7 times 3 divided by 2 pi times 1.25. And we get a magnetic field strength of 4.8 times 10 to the negative 7 Teslas. Okay, cool. Okay, cool. Let's keep on going. What about the direction of the forces between wires? Okay, so let's go ahead and think about these magnetic fields, okay? I'm going to focus in on just this wire 1, okay? So for wire 1, we have the current going up. So the field is going to be going into the page on the right side of it. And coming out of the page on the other side. Yep. Now I'm going to go ahead and extend this just a little bit. Okay. And then if we look at wire 2, it has the same direction of the current, so it has the same direction of the magnetic fields. Be into the page on this side. And out of the page on this side. So we can see at a point directly in between the wires, the magnetic fields will cancel out because they're going in opposite directions. But if we look at just wire 1, so if we look at the force on 1 due to 2, okay, 1 has a current moving in a magnetic field that's going into the page. So we can put our thumb in the direction of the current. Our finger, the magnetic field created by 2, coming out at us. The magnetic field created by 2 is coming out at us. So we put our thumb going up, the direction of the current. The magnetic field, that's this finger, remember, is going to be coming out at us. And so my middle finger, my force, is pointing towards wire 2. Okay? It's going to be going in that direction. Where my force on 2 due to 1, okay, well for 2, get our right hand again. The thumb is going in the direction of the current. The magnetic field that it's in is going into the page, so its force is to the left, okay? So they're both creating magnetic fields that the other wire is experiencing. And then because moving charges are affected by magnetic fields, they feel a force that pulls them together. And we say, flow together, go together. If we have 2 currents flowing in the same direction, their forces are going to attract them towards each other. Where, is that the case for it if they're going apart? No, you guys know that. But let's go ahead and look at it. So I'm going ahead and drawing the field due to 1. It's in the same direction that it was on the other one. But for number 2, now the current is going in the opposite direction. The current's going downwards, so we curve our fingers. They're going to be going into the page on the left side and out of the page on the right side. So in this case, the fields are being amplified by each other, okay? Both of the wires are creating a field that's going into the page. So there's going to be a stronger field between the wires. But what's going to be the effect on that force? So the force on 1 due to 2, okay? Well, the current's going up. It's in a magnetic field that's going into the page. So that the index finger is going into the page. And my middle finger, my force, then is to the left. Okay. And for this one, hopefully you guys can see, it's going to be going in the opposite direction. Okay. The current's going down and it's in a magnetic field into the page. So that force is going to the right. So it's flow together, go together, and flow apart, go apart. For the force between 2 current carrying wires. But what about perpendicular wires, okay? Magnetic parallel wires will exert that force on each other, but what if they were perpendicular, okay? Well, let's go ahead and draw them, okay? So let's focus in on one first. So again, one is going up, so we have into the page on this side of it and out of the page on this side of it. And let's just look at the force on 2 due to being in that field. So we got our right hand in the direction of the current. The magnetic field is going into the page on that side. So it's going to experience a force up. Where on this side, it's in an opposite directed magnetic field. So it's going to experience a force down. Okay? You're actually going to get rotation. Okay? You get a torque on the wires. So there is a force, but it causes a rotation. Okay, cool? Okay, cool. So how do we harness this, okay? We have electricity can create magnetism, and magnetism can create electricity. We have harnessed that, okay? That was Faraday's big discovery. We can harness magnetism and use it to create electricity because we can move wires or coils through these magnetic fields. Now, if we're moving a charge or moving a wire through a magnetic field, we measure the electromotive force that is induced. It is a bit of a misnomer because it's not really a force. It's really that potential energy difference, the EMF, similar to voltage, but we call it a force. And that force is equal to the magnetic field strength times the length of the wire times the velocity. Okay, so E is the EMF or electromotive force, okay, measured in volts. B is the magnetic field. Magnetic field, normally in Teslas. L is going to be the length of the wire in the field. Now, sometimes they'll test you with this and they'll have only a portion of the wire in the field and some of it outside the field. And it's only going to be the length of the wire in the field measured in meters. And then V is going to be the speed of the motion measured in meters per second. Okay. So if we move a wire in that magnetic field, we get a potential difference, which causes that current to be induced, which creates its own magnetic field, and so on and so on. Yep. So let's look at an example and apply it. We have a 2-meter wire-long field moves perpendicularly for a 0.080 Tesla field at a speed of 7 meters per second. What EMF is induced? And then if the wire has a resistance of 0.5 ohms, what is the current in the wire? Okay, so we have our length of wire is 2 meters. We have our magnetic field strength as 0.080 Teslas. And we have our velocity of 7 meters per second. So we can just plug that into the equation. I'm not going to put in the units. Just trust me that they work out. If you need to do the derivation, look up the Wikipedia for what a Tesla is and what it's equivalent to, and you'll get lots of answers. I think it's an Ampere per meter, something like that. But trust me that the units work out with these equations. And of course, then I drew in a unit. Okay, times 7.0. We plug that into our calculator. And we get 1.12 volts. Okay. So then we can use V equals IR, or we're solving for current. So current equals voltage divided by resistance with that 1.2 volts divided by 0.50 ohms to get that the current is 2.24 amps. Yep. And then this picture is showing you what will happen, but even without a power source, okay, if we move the bar, it induces a current in the loop of wire and thus turns on that light bulb. Okay. But what is flux? You've probably heard about that before, magnetic flux. Okay, so magnetic flux is the scalar measure of the total magnetic field passing through an area. And it is in units of Webers. Okay, where technically a Weber is a Tesla per square meter. Okay, now this is a scalar measure of the total magnetic field passing through a coil. And we calculate that. There are two equations in your equation sheet for it. There is the magnetic field dot times the area, the dot product. But what that actually means, oops, not A, is that it is flux magnetic. The phi symbol is for flux, and then B means magnetic. It's going to be B times the cosine of the angle between them times A. Okay, so let me make sure that we understand kind of how this works out. And I'm going to use this little wire thing to kind of demonstrate. So I have a bunch of wires here that can move in and out. So if I have a coil that is perpendicular to these wires, okay, we can see that a lot of the little pins can fit through that wire, okay? That's going to be your maximum amount of flux. Where if I turn this and had it parallel to the direction of the field, do any of the pins fit through that circle? No. So it's going to have no flux, okay? Where if it's at an angle, well, then some of the pins fit through the circle, okay? And we have some flux. But it's just based on the angle with respect to the plane. So how do we change the flux in a coil? Well, as I was just showing you, we can change the angle or rotate it. Okay. It is also possible that we can change the area. Okay. Make the actual coil bigger or smaller. And, we can also change the strength of the field. If we change the strength of the magnetic field, we also change the flux. Okay? So that is flux. Flux is just a scalar measure of the total magnetic field in an area. Now, where this gets put together with electromagnetism is Lenz's law, is that current, that EMF, can be created when flux changes. So flux by itself does not create electricity, but a change in magnetic flux will. And that's Lenz's law. It is that the EMF equals negative the change in the magnetic flux over some unit of time. And really, I would recommend ignore that negative sign. It's to help you figure out the direction. But since we use our right-hand rule to figure out the direction, you're not really going to need that negative sign. Okay? So when that current is flowing through a loop, the current creates its own magnetic field that points opposite the existing magnetic field when the flux is increasing and in the same direction when it's decreasing. Okay? So this all goes together. So if we're changing the magnetic flux, we're inducing current, which generates its own magnetic field. But according to that conservation of energy, the direction of the induced current will always create a magnetic field that opposes the change in flux. Okay, name of the game is oppose the change. So let's look and imagine that this wire is being pulled to the right through this area of a magnetic field. Okay. First, as it's just moving, there's no magnetic field, so no flux and no current. But as it starts to enter that field, okay, as that loop of wire enters the field, all of a sudden we have our flux is going to be increasing due to that area increasing inside that magnetic field. Okay? Now, the existing magnetic field is coming out at us, out of the page. So the induced field must oppose the change. Since the field coming out of the page is increasing, the induced field will go into the page. Okay? So the induced field that is created by this coil of wire will go into the page. And what direction is current going? If it's creating a magnetic field into the page, it's creating a clockwise current. Okay, so the current induced is going to be clockwise. Current induced clockwise. Yep. Now, if that wire is just moving in a field, okay, there's no change in the flux. Okay, there's no change in the flux. So there is no induced current. Okay, where now at T4, that wire is moving out of the page. So the flux is decreasing due to that decreasing area. So we want to oppose that change. Since the flux is decreasing, we want to put it back. So the induced field will go in the same direction as the existing magnetic field. So the induced field will come out of the page. So we draw that in. It's going in the same direction as the existing one. Get our right hand. Field's coming out of the page, so the current must be flowing counterclockwise. Induced current goes counterclockwise. Well, if currents create magnetic fields and magnetic fields create current, that's how, well, do I talk about this later? No. Also a generator. This is shown with a bar magnet, but it could also be an electromagnet. Since we have that spinning magnet, we get that generation of electricity. And we could increase the electricity by increasing the area of our loops or increasing our number of loops and get more electricity there. Okay, so let's go ahead and finish it up with a couple more practice problems. So we have a circular loop of a radius 3 meters is placed within a uniform magnetic field. Okay, so we have the radius of the circle is 3.0 centimeters. I know I'm going to need that in meters, so I'm just going to put it in meters now, 0.03 meters. We know our Tesla is 0.20, or our magnetic field is 0.20 Teslas. And originally the loop is perpendicular to the field. So when it's perpendicular to the field, we call that angle a 0-degree angle, okay? It's measured with respect to normal. So perpendicular is going to be a 0-degree angle, meaning cosine of theta is at its max, okay? It's going to be 1. So let's go ahead and calculate the area of our coil because we're going to need that. The equation for the magnetic flux is magnetic field times cosine of theta times A. So I know I need my area. It's a circle. So the area of a circle is pi r squared. So we got 0.03 squared times pi, which gives me 0.0028. So plugging that into the flux equation, we have 0.20 Teslas. Cosine of 0 is 1. So the times the area of 0.0028 meters squared gives me 5.6 times 10 to the negative 4 Webers. Okay. Oh, and it looks like Weber's is Tesla meter squared, not Tesla's per meter squared. Did I say that wrong up above? Yes. Okay. It's Tesla meter squared. And something that's kind of fun if you're curious about like derived units like that is if you go to the Wikipedia page for the Weber unit, you get all of the other things that it is equal to. Okay, we got it in joules, we got it in coulombs, we got it in kilograms, in meters. Okay, we got it in volts times seconds. There's a lot of different units for the Weber. Yeah. Okay, cool. So what would be the magnetic flux if the loop were rotated 45 degrees? So we can go ahead and plug that in, 0 and 45. That's going to be a 45-degree angle. So our flux will be 0.20 times the cosine of 45 degrees times 0.0028. And we get 0.20 times the cosine of 45 degrees times 0.0028, which gives us 3.9 times 10 to the negative 4 Webers. Okay, so less force. And if it were rotated 90, wait a minute, what's the cosine of 90 degrees? Okay, you guys know that from stats? Well, then the coil is going to be parallel to the field. So we would have no flux. Okay, cool. Okay, cool. One last one. That circular, two last ones, I lied. That circular loop rotates at a constant angular speed through 45 degree seconds in 0.5 seconds. So what is the induced EMF in the loop? Well, the induced EMF is the change in the magnetic flux over that time. So we have our final magnetic flux, constant angular speed through that 45 degrees. So when it hit that 45 degrees, it was at 3.9 times 10 to the negative 4th Webers, where it started at, up there, 5.6 times 10 to the negative 4 Webers. And they're saying that all happened in a time duration of 0.5 seconds. So we can plug that into our calculators. And we get 3.4 times 10 to the negative 4 volts. A very small amount of current, okay? One little coil doesn't give you much current. You need hundreds and hundreds of coils to get measurable voltage and current. And which direction? So let's go ahead and picture this. So we have, let's go back up to that diagram. Okay, we have the coil here and the magnetic field is going into the page. Okay, so we have that coil and the magnetic field is going into the page. And we're also saying that the flux is, or the magnetic field strength in that wire is decreasing, okay? Because as that goes to 45, that is decreasing. So if the magnetic field is decreasing, that means the flux is decreasing. So the induced field wants to be in the same direction as the existing field. So the induced field needs to go into the page. We grab our right hand, we put our thumb into the page, so the current is going to go clockwise. To create a magnetic field going into the page to replace the one that it's losing as it rotates. Okay, and one last problem. So we have a square loop of wire, 2 centimeters on each side. Okay, so square loop, 2.0 centimeters on each side, contains 5 tight turns. Okay, so there's 5 times the coils, and has a totally resistance, that probably should say total resistance, of 0.0002 ohms, 2 times 10 to the negative 4 ohms. It is placed 20 centimeters away, okay, from a long straight current carrying wire. So we got that. That is 20 centimeters, not to be confused with the 2 centimeters. Okay, if the current in the wire is increased at a steady rate from 20 amps to 50 amps in 2 seconds, okay, so the current is going from 20.0 amps to 50.0 amps, okay, in a time of 2.0 seconds. Determine the magnitude and direction of the current induced in the square loop. Assume the magnetic field through the loop is uniform and equal to the magnetic field at its center. Okay, so we definitely have some equations that we're going to have to put together here. First off, we're looking for the direction of the current, and we're given the resistance. So we can say that we're going to need I equals V over R, where this V is going to be the EMF created by that changing field. So that EMF is going to be created by the change in flux over that change in time. But what's creating the change in flux? Well, that change in flux is created by the change in that magnetic field strength created by the wire, which is the first equation that we learned, the mu naught over 2 pi I over R. Now, we could probably put all of those equations together and solve it in one step, but I think it's going to be easier to just solve for it piece by piece, so that's what I'm going to do. So let's start with the magnetic fields, okay? So the magnetic field equals mu naught, which is 4 pi times 10 to the negative 7, times the current, which we're going to start with 20 amps, over 2 pi times the distance from that wire, which is 20 centimeters or 0.2 meters. So the magnetic field at time 0 is going to be two times 10 to the negative 5. Now, if I do that exact same calculation at time 2 seconds, okay, same calculation, but with 50 amps, okay, other than that, it's exactly the same. We get times 50 amps divided by 2 pi times 0.2 gives us 5 times 10 to the negative 5. Okay, so we can use that to calculate our change in flux, or we can use that to calculate our flux. Okay, so then the flux at this time, flux is that times the area. So the area of that square is 2 centimeters squared. So 0.02 squared, which is 4 times 10 to the negative 4 square meters. So if I multiply that by that, we get our actual flux, which is going to be 8 times 10 to the negative 9 Webers here, and 2 times 10 to the negative 8 Webers here. So we can plug that into the EMF equation. The EMF equation is it's the change in flux over time. So we got 2 times 10 to the negative 8 minus 8 times 10 to the negative 9 Webers over the 2 seconds that it took to make that change. Gives us 6 times 10 to the negative 9 volts. Okay, and then we can plug that into our current. Okay, current equals voltage over resistance. So we got 6 times 10 to the negative 9 volts divided by 0.0002 ohms to give us 3 times 10 to the negative 5th amps. So I messed up. I missed something. I'm like, these numbers seem really small. Anybody know where I messed up? Yeah, there were 5 loops of wire. I missed this 5 times the loop of wire. So that area is actually going to be times 5. Okay, so let's go ahead and fix that up, plugging in the correct numbers here. Okay, so we have 8 times 10 to the negative 9 times 5, okay, for 5 turns, which is going to be 4 times 10 to the negative 8. And then we have 2 times 10 to the negative 8 times 5, which is 1 times 10 to the negative 7. So let's fix this. Sorry about that. Minus 4 times 10 to the negative 8 divided by 2 gives me, and it's still going to be a really small number, times 10 to the negative 8. And we plug that in here. And we get our actual answer, which is 1.5 times 10 to the negative 4 amps. So about 15 milliamps. Okay, cool.